Hello, everyone. Welcome to HE Classroom about the electrical circuits fundamentals. Today, we are going to talk about electrical resonance in a series circuits. For a series circuit with an AC power supply, it supports a resistor, an inductor, and a capacitor in a row. This circuit has something called impedance. Think of it as the total resistance to the AC current flowing through. At a particular frequency, the two reactants from the inductor and the capacitors cancel out. The circuit's impedance reaches a minimum value. Then we say that the circuit is in a state of resonance. Today, we will dig out some details about this state of electrical resonance in a series LCR circuits. The impedance can be written as Z equals R plus G times XL minus XC. Here, XL is the inductive reactance and XC is the capacitive reactance. Don't worry about the G too much. It's just a math trick engineers use to show the phase change of AC flow current caused by capacitors and inductors. Here's the cool part. This impedance isn't fixed. It changes depends on the frequency of the AC power supply. Why? Because first, the inductive reactance XL equals 2 pi times the frequency times the inductance L. If we plot in the XL against the frequency, we will see that XL starts at 0. As the frequency goes up, it shoots up in a straight line. Simple, right? On the other hand, the capacitive reactance from the capacitors Xc equals 1 divided by 2 pi times frequency times the capacitance C. Xc starts super high negatively and low frequency and then dives down, curves as it goes. The total reactance, the difference between XL and Xc, is what really matters here. And we've got that drawn as a dashed line on the graph. So what's happening? At low frequency, XL is tiny compared to Xc. So the total reactance, XL minus Xc, ends up negative and big. Means the circuit acts mostly like a capacitor. But at high frequencies, XL takes over, getting way bigger than Xc, and the total reactance flips positive, and now the circuit feels more like an inductor. Here's where it gets interesting. There's one special frequency, let's call it Fr, the resonant frequency, where XL and Xc are exactly equal. When that happens, XL minus Xc equals 0. Plug that into our impedance formula and Z just becomes R. No fancy G stuff, no reactance, just the plain old resistor. That's the sweet spot, and we call it electrical resonance. This special frequency is the resonance frequency. At this frequency, the circuit hums along perfectly balanced. Like it finds its happy place, everything lines up just right. So, that's the deal with the series LCR circuits about electrical resonance. Okay, let's do some work to see what happens above and below that resonant frequency we talked about. About impedance. The impedance Z equals R plus G times XL minus Xc. Here we have an imaginary parts with G, so we need to write the absolute value of Z equals the square root of R squared plus XL minus Xc squared. We plot the absolute value of Z versus frequency. When the frequency is way below resonance, the reactance is dominated by Xc and really big. As approaching to Fr, it drops down to its lowest points. Then, as the frequency goes way above resonance, the impedance shoots up high again because inductive reactance takes over. What we see here is that impedance is high on both sides of resonance, but right under resonance frequency, it reaches to its lowest point only the resistance of the resistor. Because the two reactance parts cancel out to zero, so the series LCR circuit has its minimum impedance right under resonance. Now let's talk about the current. How many electrons are actually flowing through these circuits? The current depends on the voltage divided by the impedance, and we've got a formula for that. I equals V over R plus G XL minus XC. Again, we have an imaginary part here, so we need to evaluate the amplitude of the current. We can write the absolute value of I equals V divided by the square root of R squared plus XL minus XC squared. Here we go. Since I is inversely proportional to R, we can find more from the frequency response curve. Away from the resonance, the current is pretty low because the impedance is pretty high. But right under resonance, where impedance dips to its minimum and the current spikes up sharply. And resonance, where XL equals XC, and these two reactants will cancel out to zero. So the current just becomes V over R, nice and straightforward. Now let's think about what's happening with the circuit's behavior. As shown in this graph, as we hit resonance, everything balanced out and the phase angle drops to zero. And frequencies way below resonance, the impedance is mostly capacitive because Xc is huge compared to XL. When that happens, the current gets ahead of the voltage by about 90 degrees. Engineers call that a leading phase angle. On the other side, and frequencies way above resonance, XL takes over, making the impedance mostly inductive. And the current lags behind the voltage by about 90 degrees, a lagging phase angle. As shown in the phase graph, it's like the circuit's personality changes as we tune the frequency. And this graph captures that shift perfectly. Okay, let's talk about how we figure out the resonance frequency in a series LCR circuit. It's simpler than it looks. Resonance happens when the inductive reactance XL equals the capacitive reactance XC. XL is 2 pi times frequency times the L, and Xc is 1 divided by 2 pi times Fr times C. So we set them equal to each other. Now, 2 pi FRL equals 1 over 2 pi FRC. To solve for the FR, then we need to shift things around a little bit. After some math magics, we end up with FR squared equals 1 over 2 pi squared times L times C. Take the square root of both sides, then we will get FR equals 1 over 2 pi times the square root of L times C. That's our resonance frequency formula. Easy, right? Now let's put this to work with an example here. We are giving L as 85 microhenry. That's 85 times 10 to minus 6 henries. Capacitor as 298 picofarads. That's 298 times 10 to minus 12 farads. R as 100 ohm and a voltage of 10 volts. First, let's find that resonant frequency, Fr. Using our formula, FR equals 1 over 2 pi times square root of 85 microhenries times 298 picofarads. Plug in the numbers, crunch it down, then you can get FR equals 1 megahertz. That's where this circuit hits resonance. Next, we are asked to calculate the current and a bunch of frequencies here. So to do this, we use the current formulas. The absolute value of current equals V divided by the square root of R squared plus XL minus XC squared. So at each frequency, we calculate XL, which is 2 pi times the frequency times L, and XC, which is 1 over 2 pi times the frequency times the C. Then plug them into this formula with V equal 10 volts and R as 100 ohms. Then we can get a table of values. I won't bother you with every step, but imagine we work it out for all the frequencies here. Here are the tables with the results filled in. Now, check this out from the table we've got. See, we start at 250 kilohertz. That's a quarter of the resonant frequency. And the current sitting at 5 milliamps. Double that frequency to 500 kilohertz and the current jumps up to 12.4 milliamps. Pretty nice, right? But now let's go above resonance and 2 megahertz, which is twice the resonant frequency. The current back down to 12.4 milliamp. Double it again to 4 megahertz, and it falls to 5 milliamps again. Here we plot those current values against the frequency on a graph. We use a logarithmic scale for the frequency axis. Why logarithmic? Because the current doesn't change linearly. The way the current changes the frequency isn't a straight line. It's not like double the frequency, double the current. Nope, it's more of a curve that flattens out. That's why we use a log scale on this graph. Plotting it this way makes the sharp peak and resonance and the steep drops on either side really pops out. Okay, let's look at this curve. Right in the middle, under resonance, the current hits its peak. It's at its maximum. But as we move away from this sweet spot, either higher or lower in frequency, the current drops off fast. It's like a steep hill on both sides of the peak. Okay, let's see what's happening with the voltages in our series LCR circuits. First, the voltage across the resistor VR equals I times R. And resonance, this is a big deal because VR actually equals the supply voltage. That's the voltage pushing everything along. How about the capacitor and inductor? The voltage across the capacitor VC is I times AXC, the capacitive reactance. For the inductor, VL equals I times XL, the inductive reactance. Here's where it gets interesting. Let's calculate VR, VC, and VL and different frequency using the same circuits. Here we have L and 85 microhenries, capacitors and 298 picofarads, R and 100 ohms, and V and 10 watts. We've already got the resonant frequency equals 1 megahertz and the current values from the table above. So just work out with these formulas to get voltage. The results go into this table. We won't run through every numbers here. Then we plot the VR, VC, and VL against the frequency on a log scale here. What do we see? Their graphs look a lot like the current versus frequency graph we talked about before. And resonance, 1 megahertz. The voltage across the capacitor and inductors spike up way higher than the supply voltage, sometimes many times bigger. We call this the resonance rise in voltage, which makes these circuits so fascinating. Besides, VR stays steady at 10 volts and resonance because that's where I times R matches the supply voltage. Away from the resonance, those VR and those VC and VL values drops off, just like the current does. Now, let's take a closer look at what's happening with the voltage in the series LCR circuits right at the resonance frequency. Here, let's plot out the voltage waveforms involved in these circuits against the time. Here, first we have Vs, a nice AC waves. Then we can plot VR and find out that VR is synchronized with Vs perfectly. They are in phase. But as we plot Vc, it chills behind Vs by 90 degrees. It lags. As we plot VL out here, VL is ahead of Vs by 90 degrees. When you see all these waves in action, it's pretty cool how they dance together. Let's take a close look. When VL hits its positive peak, Vc is at its negative peak, right at the same moments. And when Vc swings back to its positive peak, VL is down at its negative. They are like two kids on a seashore perfectly out of synchronized and cancel each other all the times. Now check out VR, the voltage across the resistor. Its positive and negative peaks line up with at different moments when VL and VC both hit zero. So while the inductor and the capacitor voltage are swinging high and low, VR peaks when they are neutral across the line. In summary, at the resonance frequency, VL and VC cancel each other out perfectly. Just VR is left, sitting there equal to the supply voltage. It's a neat little balance action, and that diagram shows it crystal clearly. What's all this telling us? There's energy bouncing around in these resonant circuits. Under resonant frequency, that energy is constantly bouncing back and forth between the inductor and the capacitors. When the inductor got it, it stores energy in its magnetic fields. Then it hands it off to the capacitor, and the capacitors will store it in its electric fields, and back again, like a game of hot potato. And this only happens at the resonant frequency. It's the magic number where the values of the inductor and capacitor line up just right for this energy swap to work. Okay, let's working on tuning a circuit to catch that resonance frequency we've been talking about. We already know that the formula for the resonant frequency is Fr equals 1 over 2 pi times the square root of L times C. So if L and C are set, the supply frequency has to match Fr to make the circuit resonate. Makes sense, right? But what happens if the frequency is fixed? It's like it's coming from a source you cannot change. Well, then you can adjust either L or C or even both until the circuit's resonant at the given frequency. That's exactly how a radio receiver works. It's such a perfect real-world example. Let's picture this. We've got the same kind of circuits we've been working with, but this time it has a tunable capacitor C. Now, think about how radio stations work. They are sending out signals at all sorts of different frequencies floating around in the air. The inductor in your radio picks up those signals. But to listen to a specific station, you'll need to tune the circuit to resonant at that station's frequency. That's where we get tunable capacitor C. It's like the dial on an old school radio. When you adjust C, you are changing the resonance frequency of the circuit to match the station you want. Once you hit that perfect spot, a resonant voltage builds up across the capacitors. That signal gets sent to the rest of the video. Let's plug in the numbers and see what we get. Starting at FR of 500 kHz, C equals 1 over 4 pi squared times 500 kHz squared times 100 microhenry. I'll skip the number crunching detail, trust me, it works out. And then we can find out C equals 1000 picofarads. Now let's try frequency of 1 megahertz. Same formula. C equals 1 over 4 pi squared times 1 megahertz squared times 100. Turn into the music or talk show you are hearing. Isn't it that awesome? Let's put this to the test with our real examples. We need to tune our circuits to resonate at frequency ranging from 500 kHz to 1 MHz. Think of it like flipping through station from a radio dial, trying to catch different stations. Our goal is to figure out the range of values for the tuning capacitors to make that happen. With an inductor L of 100 microhenry. To do this, we take our resonant frequency formula and flip it around to solve for C. After a bit of rearrangement, we get C equals 1 over 4 pi squared times FR squared times L. For Henry, do the math, then we will get C equals 250 picofarads. So what does this tell us? To tune these circuits across that range from 500 kHz to 1 MHz, the capacitors need to adjust from 250 picofarads to 1000 picofarads. That's the range you'll need for your tune capacitor to dial in any station between those frequencies. This is a real-life application of series resonance and work. Every time you tune a radio, you are using this exact principle to catch your favorite station. Okay, that's all for today. Hopefully you enjoy. See you next class.